relations between time and probability.
Thank you. Okay. Hello, everybody. Thank you for staying so long, and thank you to the organizers to offer me the honor of concluding this session. So I'll try to keep up with the time. I'll be talking about time and probability. So partly similar stuff as the previous talk, especially regarding James, but from a more philosophical perspective. Okay, so, but I'll start with a short introduction. So I want to explore what kind of time is or can be embedded in probabilistic theories, let's call them, meaning classical probability theory first to begin with, and then in various interpretations of probability, as there are several of them. Of course, I'll come to entropy and the error of time, and I'll give my views on the error of times using also James' approach, of which you have heard now. So I'll start first with Aristotle, which was already mentioned a few times today and yesterday. Okay, so the definition of time given by Aristotle, to my mind, presents like a small tension. So, okay, Aristotle thinks change is necessary for time, but he gives also the condition that time is a number of change or a measure of change. But he gives this, his sentence generalizes time by giving it a measure, which he does only at the end of physics, of his book of physics. So all the time while he's thinking about time, it seems as if he could be speaking about a kind of subjective time, implicit time, as Marko Vušić also pointed out. So I will do here discern measurable time and non-measurable time, or we could say maybe to some extent implicit or explicit time, or maybe objective or subjective. What I will try first to argue is that within probabilistic theories, this implicit time is very much present. So, which is not usual, for example, for physical theories. Like Marko said, we have a running parameter t in most of cases. So, okay, the measure is given by, in Aristotle's words, by a periodic motion of the solar system. So this is his universal measure giving objectivity or measure to time. Okay, nowadays it's the periodic motion of an atomic clock. So in physical models, we can have also, by this running parameter t, also time without change if we observe some constant variables. But of course, when it comes to measurement time, we need periodic motion, which has already been discussed. So that's what I want to say in probabilistic models, because I'll be talking about probabilistic models like scientific models to constrain the picture. I think there is present implicit kind of time, which requires only a kind of ordering. So I will explain a little bit more. Okay, classical probability is grounded on combinatorics, and so here I'll list some of the manifestations of what I want to argue. So usually when we want to probabilistic calculation, traditional, is disposed toward the future. So we are always calculating probability of something in the future. Well, at least when it comes to games of chance or the like. So from a philosophical point of view, there's always this situation of the present open to the future, kind of. So this implies a kind of direction of time. So these are all, maybe if you think, very trivial observations, but this is why I'll go quickly through them. This may be akin to McTaggart's A series already mentioned, because we have kind of presentism linked to the model, of course. Maybe it's not to be taken to the deepest philosophical level. Then we have, with conditional probabilities, we have a kind of weak link. Time is implicit in these situations as a kind of weak link between some past results and future results, which we want to of which we want to estimate the probability. So, well, I don't know about the observation about the McTaggart B series, but whatever. My point is that there is some implicit notion of time in probabilistic calculations. Then there's the example of if we calculate the probabilities of permutations of variations of time events, for example, I don't know, probabilities of different orders of friends coming for a visit on the same occasion. We can do that if we want to. So there is some implicit time used for calculation. And then, as a fourth example, time as change of probability distribution. Well, this is nothing special. So maybe after doing a test, we check the distribution of something before performing a test and after. So these are all very evident cases to me, but I want to point out that there is some notion of time present in those reflections. So I'll have a look at different interpretations of probability now and what's their relation to time, especially regarding, let's say, implicit and explicit time. Measurable and measured and non-measured would maybe be better. So frequentism, I'll start with Bayesianism, frequentism, then ergodic theory, quantum mechanics, and of course statistical thermodynamics at the end with the arrow of time. I'll try to go quicker through the first four and have a longer stop at the fifth. So Bayesianism, okay, understands probability as a degree of belief and uses conditional probability. This is specific. So we have in subjective probability theory, we always have this attitude to time. So we calculate the probability of an event on condition that something has happened before. But we can do also the inverse. So we can calculate inverse probability. So this is a very well-known phrase in Anglo-Saxon world. This term comes from the fact that we can calculate also the probability of something, that something has happened given the result we have. This is a very usual way of doing medical research. So we have the illness, we can investigate the cause. So making inferences about the past. So this is a very closely linked to temporal relation. But it's not necessary, of course. It can be events. A and B do not have to have a temporal relationship. Okay. What about frequencies probability? Okay, a little bit has been spoken about this. So the very definition of probability in the frequency interpretation involves a limit. So when we probabilities in the frequency theory are limits of the relative frequencies of events or outcomes. So in the practical world, of course, this means repeating some action to get the outcomes. So to my mind, from the philosophical point of view, this has a lot to do with time, as we have to approach the limit, or at least do a valuable amount of experiments. We have to move in time, let's so to say, do some periodic actions in time. Okay, this is so. In the frequency interpretation, on the other hand, the probability of a single event is not a valid concept. It does not make sense as because of the definition that I explained. So we have to have various outcomes which we gather together in time to have something called probability. Whereas, as I explained before, for a subjective, that is Bayesian approach, one event suffices, and there we see that we're already open to the future and disposed. Okay, so within frequency interpretations, nevertheless, we can meet the fourth kind of time, implicit time. This is change of distribution, probability or frequency distribution. So change through time, like I mentioned before. Okay, this is what I already commented on. If this limit and going to infinity, it includes time. So this is yeah, practical point, let's say. Oh, okay. Yeah, this limit is generally justified with the law of large number, or the more general term is central limit theorem. Okay. What about ergodic? Well, this is not a proper interpretation of probability, but I gave it that name for the purpose of this presentation. So the ergodic program was a movement that started at the end of the 19th century, which tried to give mechanical foundations to probability, or maybe even more specifically statistical mechanics. One of the first people to do something on this field was Boltzmann, and he identified probability in a system of molecules as the time average, so the probability of finding a molecule somewhere, or of having some property, the time average in the phase space of those molecules. For example, let's see. So the probability to find a molecule in a definite spatial region, he understood as the limit as the time goes to infinity of the relative time that the molecule spends in this region. So, or if we give this molecule a constant velocity, the probability of finding this molecule at this region is the relative volume of this region. Yeah, okay. It can be in the phase space, or it can be in the proper three-dimensional space. So what I want to underline is that this understanding of probability also includes time in the definition. Definition of probability seems kind of similar as in the frequency interpretation. Whether this is measured or non-measured time is, I'm not sure. I would say, as far as this is program which tries to give mechanical foundations to probabilities, probably measured time. So the kind of objective time present in the definition of probability. Yeah, okay, let's jump on. What's going on with quantum mechanics regarding this point? So quantum mechanics introduced, in a way, explicitly time-dependent probability distribution, meaning that probability distributions are a function of measurable time, or measured time, objective time, let's call it. So this is something that was not present in physics before. So this is another, so as probabilities got more and more into physical science, probability from its starting point with having to do with implicit time came into contact with explicit or objective or measured time. In the Bohmian interpretation, even we have an objective time measure also for individual particles, meaning this is a properly deterministic theory. We don't even have to deal with probabilities, but we can. So probabilities in this case are fully, let's say, co-determined by objective time within the theory. Okay, and finally we go to statistical thermodynamics. Okay. What I want to talk about now is, of course, the era of time. So the very well-known concept of entropy was given by Boltzmann as, in fact, kind of probabilistic concept. We heard that Cournot and later Clausius understood it as a quantity belonging to the macroscopic world. In fact, coming from works of experience as an empirical fact, but Boltzmann introduced probability kind of into this definition. So my main point from now on will be what's the relation within the concept of entropy between probability and time. Okay, yeah. It's often said that the maximization of entropy defines the era of time. Well, maximization of entropy has to do with heat transfer and empirically observed facts. So this was posed as necessary. It was necessary to include this in any thermodynamic theory. Of course, this holds only for isolated systems, but nevertheless triggered much debate about the relation of it has with time and for reversible and non-reversible processes. It was Boltzmann who gave the interpretation of entropy as that describes basically irreversible phenomena, but in the sense that time moves towards more probable states of the system But this is a law which holds only statistically. So occasionally we can have movement toward less probable microstates, but there is a high probability of system moving toward high entropy. So the formula there, I have not underlined this, but has been already said, that W in the formula is the number of microstates corresponding to a macro state. So this okay, regarding time, my main point is that this formula per se does not include time as we're used in physics, so explicit measurable time. But somehow it was taken to determine the direction of time. So what time are we talking about here? To my understanding, we are, because of probability being involved and changes of state, could well be talking about some kind of implicit time. So from this formula, we get no answer to the question, how much does it take to achieve this maximum entropy? Yeah. Okay, so a little bit more about Boltzmann entropy. As we know, there is also the Gibbs entropy, which was already presented. Okay, W Boltzmann understood as number of microstates, but we can express it also as a real quantity, as a volume in the phase space, standard normalized volume in the phase space region corresponding to one macrostate. So this is the phase space of velocities and coordinates, or momenta and coordinates, meaning for that we have a microstate with n particles. Let's say each particle has velocities in 3 dimensions and 3 coordinates. So this means 6n dimensions. So this rather long list of data would be one point in such phase space, highly multidimensional, if anybody cares to try to imagine it. Yeah, okay. So yeah, so we saw yesterday a simulation that displayed the movement of molecules, and it was said that we can use equations of motion or a Monte Carlo approach, meaning a probabilistic approach, basically to calculate the positions and velocities of particles. So this should mean that mechanical and probabilistic description should basically bring to the same result, if I understood correctly. My thought here is, okay, in a mechanistic simulation, we have a running time, of course, but then the system must evolve toward a state, so with higher entropy. So in a sense, we have running time, measured time, but on the other hand, there is a given direction of evolution of the microsystem. So this seems to me as if entropy, taken as a condition coming from the empirical world, can help us decide toward which way to evolve our system, as we know that dynamical systems are invariable with respect to change of time direction. So, for example, if we ran the simulation in the backward way, the molecules will return to let's say, more ordered state, as is usually said. So what is the status of entropy? I can very much relate my question to the presentation before me, because I want to use exactly the same point as the colleague did before. So what's entropy? So you already know what I'm going to say a little bit in advance, because already it has been talked about Gibbs's entropy. So on the one hand, entropy seems to be like a given empirical fact put into theory. On the other hand, we heard before, I won't be stopping long here, that we can introduce entropy in some other way, namely as an inferential principle. So here I try to give it a different meaning. So as I understand it, the definition, Gibbs's definition of entropy, I understand can also be used as a measure of average magnitude of probability of distribution. What do I mean by this? Logarithm of a quantity usually gives the scale of the quantity. So well, I won't go further into this. And the usual way to calculate averages of quantities is to multiply the probabilities with the quantities and then sum all over. So mathematically, this could pretty much be a formula for calculating the average magnitude of probability of a distribution, kind of. This is kind of my interpretation. So this could be an implicit measure for comparing the levels of probability present within some distributions. The colleague has gone deeper into the correlation with Boltzmann entropy, so I won't even touch this. But I just designed the graph to show that basically this definition of entropy assigns zero contribution to very probable and improbable events, and favorizes the moderately probable events. But of course, they must comply with the normalization that all probabilities must sum up to 1. So it has already been said that Gibbs, with his definition of entropy, derived his well-known ensembles. So the speaker before me said that Gibbs's entropy and Maxwell's entropy are very much connected, and this is also my opinion, so very extensively demonstrated before. So I don't have much to say here. What I can add is that also Boltzmann derived the microcanonical distribution. Boltzmann derived the microcanonical distribution using the notion of entropy. More precisely, it was called an H function, which he later identified with entropy. So, but he was very much thinking about a mechanistic picture of the microstates and what's going on. Whereas as we have heard, Gibbs is